Welcome to my presentation on comparison of augmented reality display techniques to support medical needle insertion. I am Florian Heinrich from the University of Magdeburg. Nowadays, many surgical procedures are carried out minimally invasively. For example, needle-based interventions require the insertion of surgical needles into the body. These methods are usually carried out using the freehand method, which is guided by medical image data on a monitor. The information is separated from the patient, which interrupts the attention of the interventionalist and is a mentally demanding task. To facilitate this, surgical navigation systems have been developed, which precisely guide the targeting process. They require less procedure time, less image scans, and higher accuracy is achievable. However, this information is still separated from the patient. Further improvements have been achieved using augmented reality visualizations. There, guidance information can be presented directly at the insertion site. Previous work focused mainly on the development of navigation systems. Thereby, no prior research was conducted on displaying aspects of these systems. In the past, systems have been developed for video see-through augmented reality, for example using handheld devices like in this image here, optical see-through augmented reality systems, mostly done on the Microsoft HoloLens, projective augmented reality systems, or on standard conditions using stationary monitors. Because no prior research was conducted on aspects of displaying devices, in this work we'd like to compare different hardware concepts as well as compare augmented reality systems with the standard method. So, how did we do this? At first, we developed 4 augmented reality display techniques to visualize our instrument navigation aid. The first one was a video see-through spatial display, namely a tablet PC that we mounted on a table and faced it towards a phantom that was placed on this table. The video feed captured the scene and the augmented reality glyph was visualized on the tablet. The next technique was an optical see-through head-mounted display. We used the Microsoft HoloLens to render this navigation glyph and rendered it by looking through the HoloLens. Finally, we created a spatial projector camera system. There, the projector was used to project this navigation aid directly on the patient. And of course, we implemented a monitor-based navigation system, which was based on a commercially available navigation system, so that the position of the monitor was comparable to the one that would be in the OR. Next, we designed our study. For our sample design, we considered medical students because no clinical experiences were required for our tasks, but a general medical background was favorable. We were able to recruit 21 participants, 13 of which were female. The primary task was a needle insertion at a given insertion position, angle, and depth. The image on the right shows the study apparatus, where you can see the optical tracking camera used for tracking the needle that is positioned on the table, as well as our 4 devices that were used for displaying techniques. The table also shows the phantom used for our study. Additionally, we included a secondary task to assess mental workload. We included a mental rotation task, where participants needed to decide whether a rotated alphanumeric character was normal or mirror reversed. The stimuli appeared after 5 to 15 seconds or after reaching 10% of the insertion depth. The image in the right below shows used alphanumeric characters. When participants decided whether this character was normal or mirror reversed, they needed to press a button on a handheld remote. As dependent variables, we included angular deviation, depth deviation, and task completion time for our primary task, and reaction time together with error count for the secondary task. Our independent variable was, of course, the 4 display techniques. For the procedure, 3 insertions were needed for each display technique, so each participant inserted the needle 12 times. Concepts were presented in a randomized order, and a free training phase began before a new concept was started. Our experiment was concluded with a semi-structured interview at the end. In this talk, I will not go in detail about the results of this semi-structured interview. Please refer to the paper. After conducting the experiment, we conducted one-way within subject ANOVAs on each dependent variable, except for the error count, on which we conducted a chi-square goodness of fit test. So what did we find out? First, we did achieve statistically significant results on task completion time. Here, the spatial AR projection system showed the best results, while the tablet took the longest amount of time. The depth deviation variable showed no significant results, but the descriptive data shows advantages of the projector system. Regarding angular deviation, we did find statistically significant results, again favoring the spatial AR projection system. Here, the video see-through augmented reality tablet and the non-AR monitor-based solution required the most amount of angular deviation. As for our secondary task variables, unfortunately, no statistically significant results could be achieved. This task has to be improved on in the future in order to conclude any meaningful results. So let's conclude this talk. Regarding the display techniques, the projector and the optical see-through HMD were favorable. More perceptual issues were found for the video see-through display. The standard method was subjectively described as more demanding and performed worse in objective measures. Regarding mental demand, no clear results could be found in the secondary task. A better task design is needed in future work. Our study is limited with respect to the registration and absolute targeting accuracy, which were not measured, which should be done in a future study. Regarding clinical applicability, deformation and patient movement would need to be considered. In future work, the effects of display techniques on the localization of entry points should be investigated. Additionally, a comparison to alternative display types should be done, like skin displays. The take-home message of this talk is needle navigation aids should be shown directly on the insertion side rather than require the intermediate view on screens. These are the references of this talk. With this, I would like to thank you for your attention. Bye.